Now we look at question 12. Question 12, we can see a sound wave, and once you see a sound wave, you should immediately be able to tell that for a sound wave, it is a longitudinal wave, which means that we will definitely see compressions and rarefactions within a sound wave. So let's look at figure 12.1. Figure 12.1, after the sound wave passes through, then the molecules look like this. So it's clear that in figure 12.1, we can see obvious regions of compressions and regions of rarefactions. As you can see that these are the centers of compression, which I'll label as C, and the centers of rarefaction can also be seen over here, which I'll label as R. So how does figure 12.1 show that sound is a longitudinal wave? You can immediately identify that from figure 12.1 on line Y, we can see a very important keyword, which is alternating regions. Alternating regions of compressions and rarefactions can be seen. Okay, so it is important to have the keyword alternating or a series of compressions and rarefactions that can be seen along line Y, which tells us that this is a longitudinal wave. Okay, so this is for part I. Okay, part 2. Describe the waveform shown in figure 12.1 and how it can be obtained by a slinky. So I put a picture of a slinky here in case you forgot what a slinky is. So a slinky is essentially just a very big metal spring, and how we can obtain a longitudinal wave is very simply, just push and pull the slinky along its length. It is important to specify how we are moving this slinky because it must be parallel to the direction of the length in order to produce a longitudinal wave. Okay, and for part 3, essentially, why can't we hear sound in space? It's simply because in space there is no medium or air particles that allows us for the transmission of sound. So that is the simple reason why we cannot hear sound in space. Okay, and this is for question 12a. Moving on to question 12b. Now using a data logger, I plot the displacement distance graph on this axis below here, and the question is the wave travels from left to right, and for B part I, we are asked to define the term period, which is a definition which you should have memorized. So period is simply the amount of time taken for a wave to make one complete oscillation. Okay, so from the question here, we can see that the period of the wave is 4 seconds. So meaning that this wave takes 4 seconds to make one complete oscillation or to produce one complete wave. So if I have 2 seconds, the number of additional wave produced will be simply 0.5 of a wave additionally in 2 seconds. Okay. And for part 3, if I have a wave that if compression A travels in 2 seconds, so it will travel simply in 2 seconds, the new wave will look something like compression A will simply move half a period, because we know that in 2 seconds half a wave will be produced. So compression A will simply travel 2 meters, because we know that sound wave is a longitudinal wave. So compression A from here, and we know that since the wave is traveling from left to right, compression A will originally be here, and in 2 seconds later it will travel half a wave cycle. So therefore in 2 seconds later it will move on to this point over here, which is half a wave cycle. So therefore, for B part 3, the distance traveled by compression A would be simply 2.0 meters. Okay. Then for the last part, sketch the displacement distance graph of the same wave 2.0 seconds later. So we have identified from part 2 that 2 seconds later, there will be only half a wave cycle being produced. So therefore, this entire graph we see from figure 12.2 will shift to the right by half a cycle. So if I draw this out very carefully, okay, the original graph looks something like this. Okay, so therefore the graph will shift to the right by half a cycle. Okay, and then so this is the original graph, it shifts by half a cycle. And then we know that half a cycle of an additional wave is produced. So therefore, a new half a wave cycle will be produced on the graph as well. And this will be how the wave will look like 2 seconds later. Okay, and this is for B part 4. Okay, moving on to question part C. Part 1, measure and determine the values of t, the period of the wave, and amplitude of the wave. So if we recall, you look at the question carefully. 1 cm represents 1 meter on the displacement axis, which is the y-axis, and 1 cm represents 10 seconds on the x-axis, which is the time axis. So to find the amplitude, we can start by finding period first. Period is simply time taken for successive crests or throws. So we just need to simply measure, let's say, from one crest to another crest. So for example, I see that or one throw to another throw. So let's say this is identified as a crest. You can see that this is another crest as well. So therefore, the period would be the time taken for the wave to get to the next crest. This is the period. Okay, and if you measure this correctly, you should be able to measure that this will be represented by 2.3 cm, which based on the this scaling provider over here, 2.3 cm will simply represent 23 seconds. And for the amplitude, remember amplitude is from the equilibrium position to the maximum displacement. So if you measure very carefully, you'll notice that the maximum displacement is actually this distance here. This distance here, okay? And this distance here, if you measure very carefully, it will be 1.7 cm. So therefore, the amplitude of the wave will be simply 1.7 meters. And this will be the answer for question 12.